Hi everyone, you're watching the Space Channel. Recently, in the discussion under one of our videos, I was asked a question I've heard more than once. How does communication work with spacecraft that are deep in space? For example, with Mars rovers or probes sent to the edge of the solar system. Some people are curious how this is even possible over such vast distances. Others want to know why data transmission from distant spacecraft is so slow. For example, a single photo can take several hours to come through. Let's figure it out together. Sending a signal from Earth to any spacecraft isn't a big problem. We have practically all the energy resources of Earth at our disposal, and if needed, we can scale the transmitter power to the required level. In fact, today's technology and the total output of the world's power plants would be enough to send a signal across thousands of light years. So humanity will never have distance-related problems sending a signal from Earth anywhere in the solar system. Moreover, spacecraft operate in a relatively electromagnetic silence, since there are virtually no man-made noises in space that could interfere with signal transmission. The effects of natural noise can also be filtered out. Thus, sending a signal from Earth to any spacecraft is relatively easy. But the reverse, sending a signal from a spaceship back to Earth, is genuinely challenging. First, a spacecraft's energy supply is limited, and it can't simply crank up its power. This is especially acute for spacecraft flying to the edge of the solar system, because very little sunlight reaches that far. The farther they go, the less energy the solar panels generate. In addition, the flight to the outer solar system takes many years, during which the solar panels degrade, reducing their efficiency so they produce even less energy. Such a long journey also depletes the radioisotope thermoelectric generators, or RTGs, carried by probes to provide additional power. Second, on Earth, we have an enormous amount of man-made noise. Radio and television, mobile communications, military and civil aviation signals, and much more. All of this creates interference and makes it harder to receive what are already extremely weak signals from space. On top of all that, the signal power per unit area of an antenna follows the inverse square law. It's inversely proportional to the square of the distance to the spacecraft. This means that if a spaceship moves twice as far away, the signal we receive on Earth becomes 4 times weaker. To receive such weak signals on Earth, we have to build giant receiving antennas, and the bigger, the better. In addition, to distinguish a spacecraft's signal from man-made noise, multiple antennas are built far apart from one another. If all of them pick up the same signal, then it's not noise but a probe's transmission. As I mentioned, data transmission from distant spacecraft is also very slow. But why? You might think, radio waves travel at the speed of light, so why can't a probe transmit at, say, 100 megabits per second? The point is that the maximum data rate depends on the channel's bandwidth, the signal power, and the noise level. As the probe moves farther from Earth, the noise level and bandwidth remain unchanged, while the signal power drops according to the inverse square law. Therefore, the data rate drops as well. On top of this, when transmitting data, so-called check bits are added to each byte, a kind of checksum that allows errors that may occur during transmission to be detected and corrected. This method is called error-correcting coding. Depending on the type of code used, the amount of transmitted data can increase by 1.5 to 2 times. As a result, the rate of useful information decreases even further. That's why a single image from the New Horizons probe can take several hours or even days to transmit. That's all from me. Subscribe to our channel and leave your comments. Thanks for watching, and have a great weekend.